Good afternoon, everyone. Welcome to the session. Today, I would like to talk about multi-user AR in ARKit 3. My name is Quinn Ham. I'm an ARKit engineer. I would like to show you all the enhancements we made in ARKit 3 so building a multi-user AR app becomes easy and intuitive. So you can focus on all the amazing content within your app. Are you developers want to bring more people to the AR world? Then this talk is for you. Let's begin. Building a shared AR experience is about synchronization. Like the Swift Strike video you're seeing here, not only we need to keep tracking the location of the bowling pin, but also we need to track the location of the user and their interaction with the ball. But sometimes track that information can be tricky and complicated to make it right. And that is what ARKit 3 wants to solve for you. In ARKit 3, we introduce collaborative session, which make sharing 3D content location easy. And with Reality Kit, all the game status and physics simulation can be synchronized automatically under the hood, so you can focus on your content. Let's look at today's agenda. First, we're going to introduce the collaborative session, a new way to build multi-user AR app in ARKit 3. Next, we're going to dive into some best practices for using AR anchors, especially in the context of multi-user AR. Last, David is going to introduce you the Swift Strike. By utilizing ARKit 3 and Reality Kit, Swift Strike provides a new level of multi-user AR game experience. Let's start from collaborative session. To begin with, let's recap last year's multi-user AR feature we delivered in ARKit 2, Map, Save, and Load. In ARKit 2, we deliver Map, Save, and Load, which is designed for persistent AR experience. The user can record their current AR experience and recontinue after loading the map. The same feature can also be used for multi-user AR. Within this feature, we introduced a data structure called the AR World Map, which contains map of 3D landmarks that are used for camera position tracking, and also a list of AR anchors, which represents the 3D coordinates of your virtual content. Within this example, we have a tabletop scene, and we load the AR world map on top of it. So we have several 3D landmarks on the table and 2 AR anchors. When you use this feature for multi-user AR, each user loaded from the same AR world map. Then ARKit will use the 3 landmarks within the AR world map, try to localize the device itself against the map. Once ARKit manages to do that, the user can start to see the same virtual content at the right physical location. This feature provides a good multi-user AR experience if you already pre-map the environment and also have all the anchors you need saved in the AR world map. However, any new information that ARKit gathered afterwards won't be shared. For instance, one of the users may keep exploring the table on one side and putting one extra anchor, while the other user doing the same. Those newly learned map information and AR anchors won't be visible to other users. So that makes this feature as a one-time sharing AR experience, and is not optimized for unseen environment beyond the pre-map area. And that is what collaborative session want to solve for you. Collaborative session is mainly designed for the live multi-user AR experience. All the learned map information and anchors are shared continuously throughout the whole session. That means any user can add the anchor at any point of time, and that will reflect on other users' screen. And also, every user exploring the map together, that means they are benefit each other to have the best tracking and also most consistent tracking experience. That means this feature is friendly for unseen environment. You can also use this feature with or without the map. In addition, this feature uses a decentralized design with peer-to-peer communication pattern, similar to multi-peer connectivity. Therefore, there is no host user within the session. Any user can come join the session or leave the session at any point of time without interrupting others' user AR experiences. Let's see one example. Here, we have two users running in collaborative sessions. They both start their own AR experiences. At the beginning, they both do a small world exploration and put in one AR anchor. As the user keeps exploring the environment, once they start seeing the area other users have explored before, the user can start seeing the AR anchors added by others. In this case, the first user starts seeing the yellow cube, while the second user starts seeing the purple cube. Afterwards, any anchors that added by the users will immediately show up on the other screen. Because the sharing happens live continuously, so there is no interruption for the user's AR experience. And also, even most of the existing multi-user AR app requires a host user within the session. With collaborative session, now it enables a new possibility to build a decentralized multi-user AR app. Next, I'm going to dive into more about this decentralized design and how does it affect the coordinate systems within collaborative session. In this decentralized design, there is no host user within the session. That means each user can start their own AR experiences before they start join seeing each other. So that means each user can have their own AR world coordinates. In this example, we have two users running collaborative session. Each user starts doing the small world exploration and putting one anchor on each side of the table. Then, within the collaborative session, the ARKit will transmit the so-called collaboration data, which is a piece of your AR world map information to all the other users and save it as external maps. Then, as the user keeps exploring the environment, once they start to see the same area others have seen before, ARKit will utilize those 3D landmarks in the common area and try to localize itself against the external map. When they succeed, those external maps will merge locally into each user's local coordinate. Note that at this point, users still have different world coordinates, but because our AR anchors is attached to the map, so the user can still see the virtual object at the right physical location. And that is why it is important to use AR anchor in collaborative session. So let's take a look how to use collaborative session in ARKit 3. In order to use collaborative session, first, you need to make sure all the users are in the same networking layer. This networking layer can be either multi-peer connectivity or any other alternative solution that provides reliable communication. Once they are in the same networking layer, they can transmit information to each other. Then you simply need to enable collaboration in your own AR session. Once that is enabled, your AR session will periodically generate the collaboration data, as I mentioned before. Then it is the app's responsibility to transmit this data to all the other users. That is the only new code you need to add in ARKit 3 in order to use collaborative session. Let's take a look. To begin with, you need to create an AR world tracking configuration. Then you simply set the is collaboration enabled to true. Then you just run a session.run to run your AR session. If you are using RealityKit, this is the only new code you need to add to use collaborative session. If you're not using RealityKit, then you need to implement additional 2 dedicated functions to transmit the collaboration data. The first dedicated function is AR session did output collaboration data. When your own AR session creates this collaboration data, you need to transmit to all the other users. Here, we have one example using multi-peer connectivity. If your networking solution replies a failure to transmit this data, then it is your app's responsibility to transmit this data again to make sure the data is delivered. Then, once you receive this data, you simply need to call AR session did update dedicated function to pass this received data to your underlying AR session. By implementing these 2 dedicated functions, you complete the flow to transmit collaboration data. Once the collaboration data transmission is running in the background, the transmission will happen throughout the whole session. Then, for each user, they just start their own AR experience as before. As I mentioned earlier, the shared AR experience will begin after the user can localize itself against the other user's map. When that happens, your own AR session will start to receive the first AR anchors added by others, which can be served as an indication of the beginning of your shared AR experiences. Let's look at some new properties for AR anchors in collaborative session. Within collaborative session, all the user-created AR anchors lifetime are synchronized. That means the user can add or remove the anchors at any point of time, and that will reflect to all the other users. And also, we add a session identifier to each AR anchor, which can be used as an indicator who is the original creator of this AR anchor, so your app can react accordingly. Last, only the user-created AR anchors are shared. That excludes all the subclass AR anchors, including AR image anchor, AR plane anchor, and AR object anchor. That also excludes the user subclass AR anchor, which were used to attach user data within map save and load. At the beginning, you may think this is a drawback of this collaborative session design, but don't worry. This is where collaborative session and RealityKit plays well hand in hand. By using RealityKit, you can attach your user data to corresponding entity component. Once you attach your user entity to the corresponding AR anchor, all those information will be synchronized under the hood, including all the physics simulation, scene change, and sound effects. For more information, you may want to check Introducing RealityKit and Reality Composer that we present in Tuesday. So let's take a look about the code, how to use AR anchor in collaborative session. Now, within collaborative session, when you receive AR session did add anchor dedicate function, you may want to check the session identifier to see whether this anchor is added by yourself or added by others. Same thing, when you receive the AR session did remove anchor, you may also want to check whether it's removed by yourself or by others, so your app can react accordingly. So that summarizes the AR anchor, which represents the 3D coordinate systems of your virtual object. However, in collaborative session, it is also important to know other users' position. For that, we introduce a new anchor called AR participant anchor. AR participant anchor represents other users' location within your own world coordinate. It has a high frame rate update rate, same as other users' AR frame rate. This AR participant anchor is automatically created by your own AR session when it manages to localize itself against to other users' map, which means you can also use this AR participant anchor as an indication of the beginning of your shared AR experience. By using AR anchor and AR participant anchor, you can correctly visualize other users' 3D content in your own world coordinate. So that is how you would use collaborative session in ARKit 3. Let's look at some practical advice how to start a shared AR experience using collaborative session. As I mentioned before, a shared AR experience will begin after each user localizes itself in other users' map. That means they have to see the area other users have seen before. But sometimes, depends on user's motion, this could take time. If you want the user to have shared experience faster, we have two advice. First, it is recommended to have one of the user approach to the other user to have the same camera perspective. For instance, in this example, we have two users seeing the table, but they are seeing in cross direction. Then, it's not likely for ARKit to localize themselves to begin the shared AR experience. However, if you have two users stay side by side and looking at the same direction, then it is more likely for ARKit to localize and also to start a shared AR experience. Second, while you're doing this, it is the best to have one of your user stay in map tracking status, that is AR frame world mapping status mapped. By doing this, you make sure one of the user is actually seeing the 3D landmarks that are stored inside the AR world map. Therefore, when the other user approach, it is more likely they can use those 3D landmarks to localize themselves and start the shared AR experience. Let's see one example. Here, we have two users running in collaborative session. The first user simply do a small world exploration and adding one AR anchor and stay in map tracking status. While the other user simply approach the first user and seeing the same view, then they will start seeing the same AR anchors, which is used to also indicate the beginning of your shared AR experience. This advice is also applicable for last year map save and load. So you may want to put this advice in your app to recommend the motion to the user so user can start their shared AR experience faster. So that summarizes our introduction and suggestion for using collaborative session. Our API is simple and intuitive. With Reality Kit, you only need to add a few lines to enable the experience. I encourage you to give it a try and see the new multi-user AR experience in ARKit 3. Next, I would like to talk about the best practices for using AR anchors. As I mentioned before, AR anchors are the main way to share virtual content within collaborative session. Here, we have 3 simple but effective suggestions for using AR anchor. To begin with, let's look back the AR world map. As I mentioned before, each AR world map consists collection of 3D map landmarks and also list of AR anchors. In addition, we also save collection of camera poses. Those camera poses represent the camera view when 3D landmarks are first observed. For instance, in this example, we have 5 camera poses where they are created when the 3D landmarks are first created. So with this camera view, we can segment the 3D landmarks into different groups to represent different parts of the map. Once you have those views, when the user added one AR anchor, the user will provide a global position of this AR anchor with respect to the world coordinate. However, what is actually saved within our AR world map is the relative position of this AR anchor to the one of the nearest view. It is these relative positions we're keeping inside the AR world map and also transmit in the collaborative session to make sure even if each user have different world coordinate, they still can see the AR anchor at the right physical location. So once again, that is why it is important to use AR anchors in collaborative session. With this knowledge in mind, let's look at our best practices for using AR anchor. First, always respond to the AR anchor update. As ARKit keeps exploring the map more and more, it will optimize the 3D landmarks position by fine-tuning the camera pose location. When that happens, your AR anchor position will change as well because it is attached to the view. So you need to react to those anchor update functions so you can change your virtual object position accordingly. Second, when you place your virtual object, it is the best to place virtual object near to the AR anchor, but not far away from the AR anchor. The reasoning is the same as before. When the anchor update happens, if you have virtual object far away from the AR anchor, then you could experience a large translation update to your virtual object, which is not desirable. So it is the best to place your virtual object near to the AR anchor, so you can represent the tracking quality correctly. Last, if you have multiple independent virtual objects, then it is recommended to use multiple AR anchors, so they will attach to different parts of the maps. Therefore, you make sure virtual object to corresponding AR anchor distance is small. However, if you have a scenario where you have multiple virtual objects that you want to maintain their relative distance, then it is legitimate to use one single AR anchor to represent them all, as long as they are not far away from the AR anchors. So that summarizes our best practices for using AR anchors. By following those best practices, you can utilize the best tracking quality that ARKit provides to your app. Next, we're going to move to David to talk about SwiftStrike.
Thanks. Well done. Hi, everyone. I'm David, and I'm here to talk to you about SwiftStrike, which is the new multiplayer AR experience that we developed for the show here at WWDC 2019. We were inspired by the work we did last year with SwiftShot, and we wanted to build something new that leveraged RealityKit and ARKit 3 to deliver an all-new experience. We have a tabletop version that's available as sample code now, and we're working on releasing the full version as sample code in the future. If you want to, you can also go look at last year's session about SwiftShot. I'm going to talk a little bit about a couple of things we did in SwiftShot and compare and contrast what we're doing this year, so you may want to take a look at that. Now, there's a lot that goes into building a game like Swift Strike. There's sound design, asset design, animations, all kinds of things. I'm really going to focus on 3 areas here: how we used RealityKit networking to get this shared experience up and running, the physics simulation to make sure that the game played and was fun, and also a little bit about how we designed the game around the new capabilities of RealityKit and ARKit 3. So first, RealityKit networking. RealityKit networking is based on the entity component architecture that's built into RealityKit. As you write and change components, they're automatically synchronized across the network for you, including all the physics state. You don't have to do any of that code yourself. You can also define custom components for your own app's application or game logic, and it will take care of the synchronization for you as well. It uses multi-peer connectivity as the network layer. This is built into all iOS and macOS devices. It's easy to set up and get going. And all you have to do is create that network session, hand it to the AR view object, and it takes care of the rest. That includes moving the collaborative mapping data that Quinhan talked about with the new ARKit 3 collaborative mapping. So in Swift Strike, we discovered that the best way to get things working, multi-peer connectivity, RealityKit are all hostless, true peer-to-peer systems. We discovered that for our game to really get things working, we needed to define one device as the host. It's the one that keeps track of what the state of the game is and how the physics is working. The other devices participate and provide inputs and also receive the information from the host about where the game is running. So again, about custom components in RealityKit. They're really easy to set up. You define a struct. You register the components before you instantiate the AR view, and you comply with a Swift codable protocol. That provides all the information RealityKit needs to serialize your structure and send it across the network. So here's one way we use that in the game. We discovered through playtesting in Swift Strike, it was really important to make sure that both players were positioned in their starting spot when the game starts. Otherwise, it was possible for one player to get an advantage, be closer to the ball, and kind of get it around the other user. So we have an object we call the match object. It keeps track of whether or not each player is in the starting space or not, and then decides when to launch the ball. That state is also synchronized over to the clients so that we can present instructions to them using UIKit as to where they need to stand. The component also maintains a log of all those states. There's not many that it goes through, and it helps ensure that every client will see every state as it occurs. So here's an example of that in work. We wait until both players have gotten into position before we launch the ball. Once they have, the ball launches and the game begins. Here's the code that we use to do that. First is the component we defined, the match state component. It conforms to both the RealityKit component protocol and the Swift codable protocol. We define a transition within it, and there's an array of transitions. So each device gets a full log of all the match states as they go forward and can respond appropriately. Before we get started, we register our component with RealityKit so that it is ready to start synchronizing it. That's all we need to do. Now, changes to the component on the host are automatically synchronized over to the client. On the client, we then use that. We create a match observer object that watches that component for changes and then broadcasts them out to all interested parties. We're using the Combine framework for this. It's a great alternative to using delegation and really gives you a lot of flexibility. I'd recommend looking in on some of the Combine sessions from this year. So when we were doing Swift Strike, we kind of started by bringing over a lot of the code from SwiftShot. And if you watched the session from last year, we spent a lot of time talking about how we synchronized the physics data, how we encoded it, how we really compressed it, and made it tight to limit our network usage. So here's a list of most of the classes or types that we had to implement that. Well, RealityKit does the physics sync for us. And using custom components, it can also synchronize game state for us. So we deleted all of that. Didn't need it anymore. And then we took a look at the messages that were left, which are really only about deciding whether to use collaborative mapping or world map sharing to get the game started, and only get set once. So they don't need to be tightly encoded. So sad to say, I deleted the bitstream code. That's about 1,500 lines of code that we were able to get rid of, and that's lines of code that you won't have to write anymore thanks to RealityKit networking to get your shared AR experience up and running. Next, let's talk about the physics simulation itself. That synchronization, as I said, is handled by RealityKit using its built-in physics engine. On your entities, you can configure the physics properties by setting up components. You set up the rigid body that defines the shape of the object in the scene. You define collision masks that configure which objects in your scene can collide with which other objects, and then also the additional physical properties of the object. The mass, the friction, the restitution, all of those play into getting that right to get a great experience. In SwiftStrike, the host device owns the simulation, but the client devices provide information about where each individual player is to make the game happen. And I'll talk about how that works later on. Now, in SwiftStrike, most of the objects are pretty simple. The ball's a sphere, the play surface is a plane. We put walls on the sides to make sure the ball doesn't fly out. But there's one object that we really needed to get right that's a little bit more complicated than that, and that's the bowling pin. Really needed this to bounce true and sound right for the game to be compelling. This is just the wireframe of the 3D model our technical artist provided for us. And this is enough data to make it really look great when it renders, but really it's far too much data for the physics simulation. We wanted to take this and make it a lot simpler while still maintaining a great bowling pin kind of feel. So here's kind of what we did with that. We used a combination of the primitive shapes that's part of the RealityKit physics networking, the spheres at the top and in the middle. And then we also built convex hulls around the pin to give it a base to stand on and the neck to bounce off of other things. When you're doing a physics simulation, you want to be careful to use primitives whenever you can. If you can't, make sure that your convex hulls are relatively simple. This will give you the best performance. So we spent a lot of time tuning this to get the right combination. So here's what that looked like all together in the data. But of course, on the court, you just see the great-looking pin itself. RealityKit's physically based rendering really gives it a good shine on it and makes it look great. Thank you. So lastly, let's talk a little bit about the game design. And that has three areas. Designing for people occlusion, building an on-site experience, and defining a control mechanism for the game itself. When we learned about ARKit 3's person occlusion, we knew right away that we wanted this year's game to be a full-size experience. And we designed it so that you see person occlusion happening right from the start. When you're in starting position, you see the ball in front of you, you see the other player, and you see the pins behind the other player. Right away, person occlusion is a big part of the game. Previously, building an AR experience, you had to kind of make sure that you didn't get a person between the camera and the content. And so SwiftShot pretty much had to be a tabletop game last year. With SwiftStrike and person occlusion, now you've got a lot more possibilities as to how you want to include the virtual content in your game. Now, a full-size game requires a full-size space to play it in. So we worked with the facilities team and had a custom floor installed here at the convention center for people to play on. The wood flooring not only evokes a bowling alley, but also provides lots of great feature points for the ARKit tracking. So you get a nice, stable display. We also use the image on the logo in the center of the court to position the game board properly. ARKit image anchors are used to find that location, put the board there. So every time it starts, the game is correctly positioned and people are ready to go. Now, for the AR localization, we're using a combination of ARKit world maps and collaborative data. The players start with a world map on their device that they load and get localized very quickly, and then they start sharing collaborative data after that. So they get up fast with a quick start, and then maintain that over time as the devices share the data about the world around them. Finally, let's talk about the control mechanism. With SwiftShot last year, we thought we had a pretty simple control mechanism, right? Just tap to grab, pull to release. We made it even simpler this year. You don't have to touch the screen, you just move it to push the ball. We discovered through gameplay testing that it was great if a faster push, faster movement would mean a bigger push in the ball. Give it a kick and make it really bounce past the other player. The other thing we discovered, though, in our play testing was every once in a while, the ball would roll right through you, and that wasn't great. So instead, we had an invisible physics body located where the player is. And then we discovered that we could just win the game by running around and knocking over all the other players' pins. So instead, we were using collision masks to filter that out. The ball will collide with the pins and with the person, but the pins and the person won't collide with each other. That was some of the ways that we used the networking system and the physics to really get a great experience. Now, one of the things that we needed to solve then is how do we get the input from this device moving around onto the device while maintaining control over when the paddle is active and how much force it's applying on the host. And so we solved this using the ownership support within RealityKit. When the host starts the AR session, it creates an anchor entity, as all content within RealityKit is all parented to an anchor entity that the host maintains ownership over. When the client joins, it adds another entity to the scene that we call the player location entity, using the subclassing support with RealityKit. This maintains ownership by the client, so the client can update its location with every frame. And that's parented to the anchor entity, so it appears in all the devices. As a child of that, we add the paddle entity, and it's parented to the player location entity. So as the player moves around, the player location entity location gets updated, and that moves the paddle entity, but the host maintains control over what actions the paddle entity takes. It can turn it on and off and make sure that the gameplay remains fun for everybody. So let's look at that, at how all that came together with ARKit 3 and RealityKit to make a great gameplay experience. Here again is part of the video from the State of the Union on Monday, showing everyone playing the game. And Adam is once again the winner. Now, when we were building this, we started to learn about the other things that were coming out this year. And one of those was dark mode in iOS. And we decided we needed to take that a step further. And so we implemented cosmic mode in Swift Strike. We swapped out the assets, darkened the video feed, and used some cards with billboarding effect to really give a glow effect. Let's take a look at that. Here we go. Took me a few tries to get the winner on the first try. So that's Swift Strike. So in summary of what we've talked about today, Glenn covered the new collaborative session sharing feature in ARKit 3 and how that enables much easier localization and new shared experiences. We talked about the best ways to use AR anchors to position content within your AR experience. And then we talked about Swift Strike, our new game for 2019. We've done a tabletop version using Reality Composer, and the source for that is available now. You can get more information about that by looking at the Building AR Experiences with Reality Composer session. And we're planning to release the source for the full version of Swift Strike with a future seed. For more information, you can look at our URL for the session. Quen Han and I will both be at the ARKit and RealityKit labs immediately after the session at 3 o'clock. And also, for those of you who have gotten really good at SwiftStrike, we're having a tournament on Friday at 12:30. So we hope you all come and participate and see that. Thank you.